This is Lab 7, magnetic fields. In this lab, we will be studying magnetic fields, assuming that they operate the same way that electric fields do. Previously, we've studied how electric force upon a charge is expressed in terms of the charge times the electric field it's in. So we're going to assume that the magnetic force is equal to the magnetic charge times the magnetic field. The magnetic field is expressed in Tesla, and so the magnetic charge will have units of newtons per Tesla. We know that the electric field is expressed, the force is expressed in this equation. We're going to replace this constant proportionality with one for the magnetic case. The charges will be magnetic charges, and the constant proportionality is 10 to the 7th minus 7th Newton meter squared per the square of newtons per Tesla. And we are going to attempt to determine what the magnetic charge strength is. The value for that. We're going to do that by using this apparatus, which is a balance. We're going to set up a torque on this side due to the gravitational force of this mass rider that I've placed on this small lever arm. And then we're going to bring down this other magnet such that it counteracts, it creates a torque in the opposite direction. So finally they are equal and their needle is in the neutral position. So at that point, we say that the two forces are equal. Okay, this magnetic torque is equal to the gravitational torque. And we just solve for the magnetic force. So we find the magnetic force for the condition where the mass rider is at this position. These notches here are 1 centimeter apart. This lever arm is 10 centimeters. There's 9 of these notches here. And so we're going to take data for 9 places. And then we'll replace this mass by a heavier mass and do it again. I warn you, once you get out to the later notches here, the heavier mass will not be, can't be counteracted by this magnetic force here. So you'll have less than 9 data points in the second case. But once you do that, find all this data, and you have to record the distance between these two magnetic charges here. And the way you do that, well, I'll show you that in a minute. The way you do that, once you do that, you'll take and record those, and then you're going to plot magnetic force versus 1 over the distance squared. And you'll get a fairly straight line, the slope of which is equal to 10 to the minus 7th P1 times P2. We're going to assume that the P1 and P2 are equal to each other, and so we've called this P squared. All right. So you're going to solve for P. It's simply going to be the slope divided by 10 to the minus 7th, and then take the square root of all that. Now, like I said, you're going to find that this data is not a straight line. It looks a bit curved like this. So you'll be plotting, you'll have a plot like this. And the reason for this bending is that when these things are close together, the magnetic field lines bend around so much that they actually can start to attract each other. When you get them close together, they'll actually come up. But when they're far apart, then this distance is roughly equal to this distance. And this has a contribution. This second magnet over here has a contribution to this interaction. And so you have to take and throw away these endpoint data and just take Linus over the middle data points. And once you do that, you should get some number for P that is less, on the order of 10, less than 10. Now, in order to set this up, the first thing you've got to do is remove that magnet, and you'll have to take and adjust the masses on this arm here until finally you get this lever, this balance, to remain in the neutral position. So you can turn these little screw weights until you finally achieve that. Now, balance is going to take and oscillate back and forth. You can try to stop the oscillation by letting it run against your finger or something soft. Try to dampen it. But if you see that it's oscillating 2 tick marks to the left and 2 tick marks to the right, you can assume that it's balanced. If it's 1 tick mark to the left and 3 to the right, you know it's not balanced. So once you get it balanced, then you have to take this, raise this pedestal, it screws in and out, till the ball rests upon it, and the needle is in the neutral position. Okay, once you have achieved that, remove this entirely and bring the second magnet, our magnet, down and place it on the pedestal. And now you have to record this position. You can either record the position here at the top of the bracket or below it, but record this number. This is going to be your 0 point. So that once you have this set up with a mass rider on it, and let's say, and you've got this in a situation where the 2 torques are equal and you're in a neutral position here, you can take and record this number and subtract from this number that initial 0 number you had, and that'll give you this distance between these 2 magnetic charges. So that's little d. So you're going to find all those little d's for each of these situations where the mass rider's on the different notches. And once you have all those d's, you're going to create a column of 1 over d squared that you're going to take and plot Fm against. And remember, the magnetic force is equal to this expression here.